All right, now we are recording. All right, by the time we finish up with 11.4, we will be able to find the range of a data set, which is a rough guesstimation as to the variability within a data set, but it has a major weakness. A more accurate measure of the variability within a data set is the variance and the standard deviation of a data set. And in all honesty, when you work with software packages, crunching a lot of data, those are the statistics that are usually reported, the variance and standard deviation. The range is usually not reported. And hopefully we can interpret what the standard deviation is kind of telling us about a data set. Okay? And it becomes very useful when you compare two or more data sets as far as their variances or standard deviations are concerned. The comparison of these statistics really gives you a pinpointed idea as to the differences and similarities that exist between the data sets. All right. So measures of variation are intended to help us gain a foothold on how dispersed our data is. How spread out it is versus maybe how concentrated it is around the mean of the data set. And the range, variance, and standard deviation do give us that measure of dispersion. Most notably, the variance and standard deviation do the best job, as the range has a major flaw in it, although it is a first guesstimation. The range is extremely easy to compute. That is one of the good things about the range. As long as your data is sorted, all you need is the maximum observation in your data set and the minimum value in your data set. And you basically just subtract the minimum observation from the maximum, and you have the range. Now, can anybody think of, I mean, you got to admit, the range is easy to compute. You know, it just takes into account two data points in your data set. That's both a strength in the sense that the range is easy to compute, but it's also a weakness. Anybody know why that might be a weakness? Why is the range maybe not the best measure of variability within a data set? Anybody got any?
Because it's not accurate, it's a guess, it's an estimate. I don't know.
Well, it only takes into account how many data points in the data set in its computation. Only takes into account how many observations?
One.
Well, to compute the range, we have to know how many observations from a data set. We got to know the what value and the what value.
The highest and the lowest?
Yep. Like I said, that makes the range easy to compute, but the problem with the range, only using two data points to try to give us an idea as to the overall variability that exists within a data set, does a very poor job, because it's totally insensitive as to what's happening in between the max and the minimum values in your data set. It could care less. It's almost as if all the other data points in the data set don't even exist. Only the minimum and maximum exist. Well, ladies and gentlemen, there could be a lot of things going on in between the maximum and minimum data points as far as the dispersion is concerned. So the range misses all of that. So the range should just be used as a rough first guesstimate of variation in a data set. It's not a robust measure of variation. All right, but nonetheless, let's see if we can compute the range of some data sets here. The first list below is the weights of the dogs in the first picture, and the second is the weights of the dog in the second picture. Find the mean, median, and range for each list, then describe any observations you can make based on the results. So the first list consists of the weights of these dogs in pounds. The second list consists of the weights of all these dogs in pounds. All right. For the first list, we can compute the mean by just adding all the observations up and dividing by 4. And we get a mean weight of 65.25 pounds. The ordered list for list 1 would be 58, 60, 70, 73. So the median is the average of the middle two values, which is the mean of 60 and 70, which would be 65. So the median is 65. Notice the mean and the median are very close to being equal to each other here. Okay. And the reason why that is because this data set does not appear to have any outliers in it. An outlier, again, is a data point that is either uncharacteristically much smaller or much larger than all the other data points. The range is 15 pounds. That's just the maximum value of 73 minus the minimum value of 58. Here's the second list of weights. The mean weight of the second collection of dogs is 64 pounds. So the mean of the second group of dogs is very similar to the mean of the first group of dogs. Notice that. If you order these data points from smallest to largest, left to right, you can easily find the median, which is going to be the mean of the middle two observations of 55 and 60, which turns out to be 57.5. Okay. Notice for this data set, the mean is a little bit larger than the median and is not, nearly as close to being equal to the first data set, where the mean and median were almost numerically equivalent to each other. I think the reason stems from the fact that we do have a dog in this second data set that has a weight of 125 pounds. That seems to be a little bit larger than most of the other weights, or the majority of the other weights. Now, whether that qualifies as being an outlier or not is not 100% clear, unless you actually conducted a specific test to determine if it's an outlier. But you got to admit, 125 pounds appears to be a little bit larger than most of the weights here. For that reason, that's probably pushing the mean a little bit further to the right of the data set than the median is. The range is 95 pounds. Okay. Notice the ranges are a lot different between these two sets of weights. 15 pounds for the first collection of dogs, 95 pounds for the second collection of dogs. Why is that? Well, if you just take your eyes and glance through the weights of the first group of dogs, it looks like in general the variation of these data points is rather small. There's not much variation, but for the second group of dogs, we have a lot more dispersion within the data set, going from 30 all the way to 125. So these data points in general tend to be a little bit more dispersed or farther apart from one another. And that's why the range is at least doing a little better job in helping us to understand the differences between these data sets. So there is a little bit more variation in the weights of the second group as opposed to the first group. But like I said, the range is insensitive to all the data values in between the max and the min. And because of that, statisticians wanted to come up with a statistics that is more robust, more sensitive to all the data values within a data set in trying to express the variance or the variability. So they came up with two statistics here, variance and standard deviation. Now, the variance is actually the square of your data values in your data set. And because of that, the units of the variance are drastically different than the units of our data set. For instance, if we collected a data set that consists of measurements only in feet, well, the variance units of measure is going to be square feet. And there's a night difference between feet and square feet, ladies and gentlemen. So to bring the units back down to the same units of the data set, we take the positive square root of the variance to generate the standard deviation. And so when you take the square root of like square feet, it brings the square feet back down to just feet. So it's the standard deviation of a data set that has the same units as the values in the data set. The variance does not have the same units as the data points in a data set has. But nonetheless, you have to compute the variance first before you can then take the square root to determine the standard deviation. So how do we find the variance standard deviation of a data set? Well, step number one is we need to find the mean of the data set. Then what we're going to do is subtract the mean from each data value in the data set. We're then going to square all these differences in step two. And then in step four, we sum up all the squared differences. And then in step five, we take the sum of the squared differences and divide by n minus 1, where lowercase n is the size of the sample, to get the variance, where n is the number of observations in the sample again. To generate the standard deviation, we take the positive square root of the variance. So in a sense, the variance is kind of like, it's like an average of the squared differences that exist between a data point and the mean of a data set. All right, here's a specific sample to illustrate or breathe life into these steps. Suppose we wish to compute the variance of standard deviation for the weights of the 8 dogs in the second group of dogs we've seen earlier. The weights are listed again for the reference in order. Well, these weights are not in order, excuse me. But these are the weights of that second group of dogs in pounds. So how would we find the variance? Well, first we have to find the mean of this data set. And the mean was 64 pounds. Then we're going to subtract the mean from every data point in the data set. So 30 pounds minus 64 pounds is the difference of minus 34 pounds. 85 pounds minus 64 pounds, 21 pounds. 40 minus 64 pounds, negative 24 pounds. 125 minus 64 pounds, 61 pounds. 42 pounds minus 64 pounds, negative 22 pounds, etc., etc. We're then going to square all of these differences. And when you square a number, it always comes out as being a positive number. Okay, are we following what's going on here so far, ladies? First, we find the mean of those dog weights, of these dog weights, and it comes out to be 64. We then subtract the mean, 64, from each data value in the data set. Then we square those differences. So do we understand what's going on so far up to this point? Now we're doing all this in order to compute the variance and then ultimately the standard deviation. All right, so what are we going to do with all these squared differences now? What do you think we're going to do with all those squared differences?
Find the sum of the squares.
We're going to add them up. Yeah, we're going to sum them up. So we're going to take, 1156 plus 441 plus 576 plus 3721 plus ... plus all the way up to plus 81. So we add up those square differences, and then we divide this sum by the sample size minus 1. That is to say, we divide this sum of 6,596 by 8 minus 1, or 7. And we get a variance of 942.3. But like I said, ladies and gentlemen, these units are going to be not pounds, but the units of the variance are square units. So this is going to be square pounds. So in our minds, that doesn't make any sense. We don't even know what a square pound is. So in order to bring the square pound units back down to the same units that data values possessed, we take the positive square root of the variance and we generate the standard deviation, which brings the units down from square pounds back down to pounds. So the standard deviation is 30.7 pounds. So in a sense, ladies and gentlemen, the standard deviation is kind of like, and this is very important, so much so that I'm going to actually type it out So what is the standard deviation? Standard deviation is the average, okay, the average distance a data point is away from the mean of the data set. There you go. That's what a standard deviation is. It's an average. It's an average of the differences between a data point and the mean of the data set. So it's the average distance that a data point tends to stray away from the mean of the data set. So in general, the greater the standard deviation, the greater this deviance would be. The greater distance data points tend to stray away from the mean of a data set. The smaller the standard deviation, the smaller this deviance would be. The smaller the distance would exist between a data point and the mean of the data set. Okay. Now, symbols. In statistics, the universal symbol that is used to represent the variance of a sample is lowercase s squared. That's the symbol to represent the variance of a sample. For a population, the symbol that represents the variance is lowercase sigma squared. So whether we call this a sample or a population will dictate what the symbol we use to represent the variance. And when you take the square root of s squared or lowercase sigma squared, you're going to get the standard deviation. And so therefore, it's universally accepted in all stats books that lowercase s, which is the square root of s squared, or lowercase sigma, which is the positive square root of lowercase sigma squared, is the standard deviation of either a sample or a population. So lowercase s represents the standard deviation of a sample. Lowercase sigma is used to represent the standard deviation of a population. So a little bit about the symbolism here. And like I said, these symbols are universal, textbook to textbook. Any stats book you break open, you'll see those symbols represent what I just indicated. Okay. So s squared or s pertains to a sample. Sigma squared, sigma, pertains to a population. So s and s squared are statistics, while lowercase sigma and lowercase sigma squared are parameters. Any questions about that slide? Now, in order to, go through all these steps, because, you got to admit there are quite a few steps here. You might want to make a table to help you compute intermediate results. And this table normally has 3 columns. The first column is the original data column. The second is the difference between each data value and the mean of the data set. And the third column represents the squares of all those differences. Okay, so for instance, if you look at that second group of dogs and their weights, we can organize them in a table. The first column is the raw data column. X in pounds. The second column is the difference between the weight of the dog and the mean weight of all the dogs in the data set. And the last column takes these differences between a dog's weight and the mean dog weight. It's going to be, you're going to take the difference between the actual weight of a dog and the mean of all these dog weights, and you're going to square that difference. So you generate this last column. Now to get the variance is pretty simple. All you got to do is just sum up the last column. So when you sum up the last column here, you're then going to take the sum of the last column and divide that sum by n minus 1. And when you do that, you have the variance Okay, you got the variance of the sample. Now, if you take the square root of the variance, then you generate the standard deviation. And the only difference between these symbols and the symbols used for a population would be, instead of S squared, we would have the variance of a population being lower sigma. Lowercase sigma squared, which would represent the variance of a population. And then if you take the square root, the positive square root of lowercase sigma squared, you generate the standard deviation of a population, which is just lowercase sigma. Okay. But we were referring to these dogs in this group to be just a sample. So we would use S squared for the variance and S for the standard deviation. All right. All right. So again, this is elaborating on the steps that are used to compute the variance of a data set. Computing the mean. You obviously need the mean if you are to compute, in general, the average of the distance away from the mean that every data point experiences. And that's why we undertake these steps in this particular order. Okay. Notice the variance is always going to be positive since you're squaring differences, and the standard deviation will always be positive too. Never will a variance or standard deviation be negative. Okay. All right, so ladies and gentlemen, this is a formula for, in general, how to compute the variance of a data set. Lowercase s squared is the symbol used to represent the variance of a sample. And notice, to generate the variance of a sample, we sum up the squared differences that exist between a data point x and the mean of the sample x bar. And then we take those summed squared errors and divide that sum by the total number of observations we had in our data set. When you do that, you'll get the variance of your data set. And then you can take the square root of the variance and generate the standard deviations. So you can really see this is kind of like an average, okay, of the squared differences that exist between any observation in a sample and the mean of that sample. All right, here's an example. The mean and standard deviation of the heights of all adult males in the United States are 69.3 inches and 2 inches respectively. I got a question, ladies. Why can you name some let's say some things in the real world that would be concerned with the heights of men? Anything?
First
Anything?
thing that comes,
What's
first
that?
thing that comes to mind is roller coasters.
Yeah, roller coaster rides. There's a lot of other things. Though. Can you think of some other things? Why would we care about the average height of all men in this country? Why would we care? Yeah, roller coaster rides obviously take height into consideration at amusement parks, but there's a lot of other applications or need for knowing the average height of, let's say, a certain groups of people in this country. And can you think of why other things that would be concerned with heights?
What about building homes, doors and things like that?
Doorway heights. Where you're going to put the outlet for a shower in a house. Even the height of a toilet. Do you agree? Any other applications? That's a good example. Anything else that would be concerned with heights?
Clothes.
Clothes. Oh, heck yeah. Fashion industry. Anything else? There's a lot of application, a lot of need to know average heights. All right. Who was just on strike recently?
GM employees.
What's that? What corporation was just on strike recently?
GM, I think.
Yeah, auto industry. Building cars, ladies and gentlemen. Do you agree? For leg room, for height clearance for the head in the vehicle's compartment. All that needs to know average heights of who they're building cars for, cars or trucks for. Airlines. Do you agree? Airlines, before they build an aircraft, they want their customers to be comfortable on a flight. So heights. Yeah, there's so much need to know average heights for many different things. So this is important stuff. All right. Anyways, the mean and standard deviation for heights of all adult males in the United States are 69.3 inches. And 2.8 inches would be the standard deviation height. Okay. So what can we conclude from, this standard deviation of 2.8 inches? If you're going to, let's get back to the house, you're trying to build a house here. What height of a doorway would you want to construct? How could you use these two statistics here to help you to build a doorway that would, in a robust sense, allow everyone to pass underneath it without having to duck in general? In other words, how high would you want to build the doorway based on these two stats? Anybody? I mean, would we build the doorways exactly 60, maybe 69 inches tall? That's no good, because 3/10 inches is added on to the average. So the doorway in general on average will be what? Too short, not tall enough. So would we build a doorway 70 inches? What do you think? Exactly 70 inches tall. You think that's going to work for everybody? No, that's going to fall short a little bit too, because if you add the standard deviation of 2.8 on to 69.3, you're looking at about almost 72 inches. Do you agree? And because of that, ladies and gentlemen, you want to allow, for that standard deviation to be potentially added on to the average height. So, you'd probably want to construct a door here that's going to be at least maybe 72 inches tall. Do you agree? That way, you can rest assured in general Just about everybody will be able to pass on, through the doorway without having to duck. So it's good to know the standard deviation too, because it gives us an average measure of how far away data values tend to stray away from the mean of a data set. And that's important in, like I said, designing the heights of doorways, designing leg room or heights of vehicular cabins or aircraft cabins, okay? So all this is very important. Now it says the mean and standard deviation for the 2021-2022 Cleveland Cavaliers, which is a professional basketball team, on the other hand, were 77.4 inches and 3.75 inches for the standard deviation. Now we have a problem. Do you agree? I mean, if you build a doorway that's, 72 inches tall, granted, that's usually going to accommodate just about all the average Joes, right, that exist in the populace. But then you got your basketball players here, ladies and gentlemen. You got people that are taller than 72 inches. These people might have to duck. Do you agree? Or if they have a house built, they may insist, and probably would want to insist, that their doorways are built, a little higher than normal to accommodate them. And that goes for other fixtures in the house too. So all this stuff is very important to know, if you're going to construct, houses or cars or planes or trains or whatever it might be. It's important to know this stuff here. So statistics is very important. All right. Here's a couple of things that the author gathers from the statistics on the previous slide. The top scorers for the basketball team tend to be a lot taller than the average people. And in general, that's usually the case in the NBA. Most of the players are taller than the normal person. Not all of them, but most of them are. If you've ever watched a basketball game, this comes as no surprise. The second, the heights are spread out a bit more than the population in general. The reason why that could be is because basketball players probably come from a smaller sample size, as opposed to, if you're building houses in general in this country, you've taken into consideration maybe millions and millions of people and their heights. Okay, and therefore your dispersion is going to be a little bit less in that case about the mean, as opposed to if you have a smaller, more specialized sample. All right. So in general, we're also learning something, that if your sample size is small, your standard deviation, okay, is usually a little larger than if you have a very large sample size. So if you want, to construct something, you want to make sure you choose an appreciable sample size to get a more accurate assessment as to, how much wiggle room you have, so to speak, about the mean of that data set in constructing something. All right, here's an example, interesting example. Professor has two sections of Math 115. This wouldn't be me, by the way. This semester, the 8:30 a.m. class has a mean score of 74% with a standard deviation of 3.6%, while the 2 p.m. class, the afternoon class, also has a mean score of 74%, but with a standard deviation of 9.2%. What can we conclude about the students' averages in these two sections? Does anybody want to weigh in as to the differences that exist between the average, the course averages, and between the academic achievement of these two courses?
Could it be more people in one class?
It could be, yeah. That definitely could be the case. You definitely could have a disparity in the class size between the morning and afternoon. What if I threw this out? What if we knew for a fact that we had equal class sizes between the morning and the afternoon section? What would we then conclude about the differences between these you know, these mean scores here. Suppose we had the same class size. Then what would we conclude as being the differences? What would be the main difference between the morning and afternoon section if they did have the same size class? I'll give you a hint. The answer lies in the standard deviations. Okay, so what's the difference here? Are the standard deviations the same? No, they are not. So can anybody tell me how we would use the standard deviations, namely the differences between the standard deviations, to more accurately assess the performance of the morning versus afternoon class? Let me ask you this. Which scores are more spread out about the mean, morning or afternoon?
Afternoon.
Afternoon. Scores are all over the place. Do you agree? In general, with the afternoon group as opposed to the morning group. Does anybody want to go out on a limb and maybe conjecture as to why that might be? Why such a huge spread in the scores for the afternoon group as opposed to the morning group? Anybody want to just maybe try to maybe come up with maybe some reasons why that might be? Why would that be? Why would that be? Especially if we had the same size class. Why would there be why this difference here? What's up with this?
Test scores higher.
Yeah, some of the test scores are higher, but some of the test scores are lower. Do you agree if you have a great dispersion within a data set? Actually, this question should be posed probably more accurately towards instructors as opposed to students. All right, I can attest, ladies and gentlemen, from experience that usually morning students at institutions usually are the younger age group students that tend to be right out of high school. Okay. When you get into the afternoon and evening classes at educational institutions, a lot of your students tend to be more, let's say, more diverse in ages. Okay. In large part because, well, let's see, in the morning, most people are at work. Do you agree? The older age groups are at work. And they can only take classes maybe in the afternoon or the evening. And so when you teach like an evening class as opposed to a morning class, you can have a huge diverse range of ages for your students. I've had students anywhere from like 18 years old all the way up to like 58 years old for evening classes at various institutions over the years. So there's a larger range of ages. And because there's a larger range of ages, and you got to understand, that some of these people are maybe tired from their day job, and then they come to school in the evening. So they may not be as intellectually sharp, because they might be just fatigued. It happens. Because of these differences, age differences, and the level of alertness throughout the day, that's in general one large excuse as to why these scores are more spread out, okay, for an afternoon, evening class about the mean as opposed to a morning class, which is more homogeneic as far as age is concerned, okay, and alertness is concerned too in the morning in general. So I think that's a large contributing factor right there. Right. There could be other factors too, but I think that's a large one there, because in general, I have noticed down through the years that the student body is a little different between morning classes as opposed to afternoon, especially evening classes. I've noticed there is a difference in general. Alrighty. Okay. All right. So, yeah, when you have a large variation or a large standard deviation in a data set, that means that you have your scores are all over the place. They're spread far away from the mean in general. You could have very high scores and you could have very low scores. Okay, a large range, if you will. Okay, a large spread about the mean. As opposed if the standard deviation is small, then most of the scores tend to just clump up right around the mean. Okay. All right, ladies and gentlemen, let's go see if we can have some fun in our textbook now. Pay a couple bills today. And okay, 115, Alex. Yeah, these problems will be coming out of section 11.4. All right. 11.4. 11.4 is entitled Measures of Variation. And if you get a chance, you're welcome to look down through this, this section. There may be a couple things that are different than the PowerPoint presentation. So it's always wise maybe to just to touch base there. Okay, here we go. Now, look at problem number 13 here. It says 10 used trail bikes are randomly selected from a bike shop, and the odometer reading is recorded as follows. Okay, wait a minute. What's an odometer? What is an odometer? And what does it do? Anybody? Be nice to know what is it?
What speed you're driving at?
Odometer's mileage, isn't it?
Yeah, I think your speed, the speed indicator would be a speedometer. An odometer, I think, yeah, you're correct in saying it measures the amount of mileage that that an object travels. Okay, whatever that object is, a plane, train, automobile, bike. They even have odometers when you're walking. Do you agree? Don't they have like watches that can keep track of the distance that you walk during the day or something? They got that ability? I think they do, don't they? Watches that could do that. I don't have one of those watches, but I think they exist, don't they?
Yeah, like Fitbits and Apple Watches.
Yeah. Now, hey, do you got one of those? I'm just curious.
Do not know.
Because I'm just wondering, does anybody have one of those? Does it keep track of the number of feet that you like walked for the whole day, or what? Because I don't have one. I'm just curious. Do they?
Yes, it does.
They do record that. Interesting. The number of feet. Now, here's a good question. How does the darn thing work? How does it know? How does it do that? Does it have GPS on board? Does it tap into a satellite in space in orbit?
I think it's got the GPS, but it also tracks your movement, like arm movement.
Arm movement.
And your cardio and stuff.
Oh, okay. So maybe it looks like, I mean, if your arms are moving and your cardio has elevated, your beats per minute has elevated, then I guess it views it as being like what? Maybe you're walking or moving.
Right. Yeah.
Okay. Oh, that's weird. All right, but because that would be cool. You know where one of those would be cool? Is like if you go to an amusement park, let's say you go to Cedar Point, okay. By the end of the day, it feels like your legs are about to fall off. Okay, so you wonder, I mean, how many miles do you walk? When you're at Cedar Point for a whole day. I always wondered about that. My guesstimate would be maybe 5 miles or something. I could be wrong on that, way off on that, but I don't know, but that'd be neat to have one of those little watch things that could keep track just to kind of see how many miles you maybe put in when you're at an amusement park, just, enjoying the day. But anyways, this odometer here records the number of miles. I am assuming it's miles. I don't know that for sure. These could be in kilometers, couldn't they? So we really don't know much about these numbers here in this data set. I mean, I don't know if these are miles or kilometers or feet, yards. I don't know, but bottom line is they all have the same units. So the playing field has been leveled. Okay, that's the important thing. Anyways, ladies and gentlemen, what I would like you to do is I would like you to take this data set and I want you to find the variance and the standard deviation. Now, hold on a second here. This is what I'm going to do here. That's number 13. I'm going to go back up here and get the formula for the variance right here. And I'm going to snip that thing. And I'm going to bring it down to the problem so we can see that and have this at our disposal. We can see this here. I'm going to bring this down to number 13 now. So we'll be able to see the formula we need to compute the standard deviation and the variance. Remember, the standard deviation is the positive square root of the variance. All right. So hold on 1 second here. Yeah, so therefore I will put this formula right there, and I want us to manually compute the variance, S squared, and then the standard deviation of this data set. Now, what's the first thing we need to know from this data set? Anybody? The first thing we must compute must be the, do we remember? We got to know X bar. And what's X bar? X bar is the mean, correct? So we got to compute the mean. Then we can make a table with those 3 columns. The X column, the X minus X bar column, and the X minus X bar squared column. Okay. All right, go ahead and see if you can find the standard deviation and the variance and the standard deviation for this data set. We'll call that classwork number 1, number 13. All right, so if we wanted to compute the variance and the standard deviation in this data set manually here, first of all, we're gonna have to know the mean of the data set. We gotta add those 10 observations up and then divide by 10. So the mean odometer reading would be 716.6. Now, to compute the variance and then the standard deviation, I made a table to help out with the intermediate calculations. First column is the X column, which is the raw data column. Second column is the difference between the data point and the mean of the data set. So some of these observations are positive and some are negative. The third column takes the second column and squares all these differences. All the differences are squared, so obviously you're not going to see any negatives in this column, because when you square a number, it always is positive. Then I summed up this last column, which is the sum of the squared differences between X and X bar, which is a big number here. What is that? 3,943,022.4. Then I took this large number, the sum, and divided it by n minus 1, which is to divide it by 10 minus 1 or 9. And it gives me 438,113.6. That's the variance. When you take the positive square root of the variance, you generate the standard deviation, which is 661.9. All right. Did anybody get anything like that? Anybody get anything like that?
That came close.
Pretty close, huh? All right, good. Better than nothing. You can see how tedious this is, ladies and gentlemen, to do these calculations. This was the manual way of doing everything here. And it is very time consuming. I mean, this is just 10 observations. Could you imagine if you had to do this, compute the variance and standard deviation for maybe like 10,000 data points? That would take a long, long time. Not only a long time, but your chance of making a mistake would be greatly heightened. In such situations, we have large data sets. You really need to have a software program and a computer system. That's your only hope. Okay. Now, so the standard deviation is saying on average, any one of these odometer readings tend to stray about 662 units away from the mean on average. Again, I don't know what units they use for these mileage measurements here. I mean, for these odometer readings, it could have been in miles or kilometers or any other type of unit. I'm not sure. But the important thing is that we at least see how to compute the variance and the standard deviation. So I have a question. What would be the range of this data set? Well, that's going to be the maximum observation minus the minimum observation, correct? And what would be the max and the minimum observation in this data set? What would be the smallest observation? Well, let me say this. What's the biggest observation? Let's go with that first. Appears to be what? 1902, I believe. Is that correct? What's the minimum observation in this data set? Looks like 103. So that will be the range when you subtract the min from the max. That's going to be 1,799. That's the range of the data set there. Okay. Now, there was also a way in which we could have computed the standard deviation having used our calculator. So if you got the TI 30 or the TI 34, it's done essentially the same way. First, you have to load up a list with the raw data. Okay. So you would put the you'd put the data in a list. Now, you hit your data key. This is on the TI 34 here. You hit your data key here, and then you can populate a list here. Now I'm not going to throw all these data points into this list here, but let me just put some data values in this list and just show you how to compute the variance, or excuse me, the standard deviation. Once you load up your list, you then hit your stat button. Well, above my data key is the word stat, so I have to hit the second button followed by the data button to get into stat mode. Then you select the one-var stats function. And then you select the list that you wish to compute the one variable statistics for. It would be list 1 in my case. Leave the frequency at 1. Go down to calculate. Hit enter. Of course, you got X bar, that's the mean of your data set. S of X, ladies and gentlemen, is the standard deviation of a sample. Lowercase sigma sub X is the standard deviation of a population. You can see there's a slight difference between the two. That's because the formulas are a little different. We're considering these to be samples though, so you would want to use S of X. Now that would have saved you a ton of time on this problem if you just enter it in the X data in the list 1, and then use the one-var stats function to find the standard deviation of this data set, instead of having to go through all this. So you can see that this calculator can do a lot of work in a very short period of time. All right. So let's see if you can maybe on this next problem use your calculator to do problem number 19. Does anybody got a TI 84 calculator in here? Anybody? TI 84 calculator. Nobody has a TI 84? All right. Well, number 19. The table below shows the average price of gallons of regular unleaded gas in the United States, in US dollars, excuse me, for various countries in January of 2022. So we have our data set here. Gas prices from around the world. I'm assuming these are average, average gas prices here? Yeah, average price of gallon of regular.
Excuse me, I just want to know, is it possible for you to show us how to put it inside the calculator? Because even when you were showing it, and I have a TI 30 because that's what the course said it needed. Mine just looks a little different.
The TI 30 looks a little different?
Yeah.
Well, we got a data button, correct?
Yes.
And you also have stat above your data button?
So my button above mine, it says delete.
This is the TI 30 XS right here. And you can see that it does have a data button here and above stat button.
Okay, I do.
But is it, you got this calculator? Is that the one? Or?
I do have that one, and I do see that it says stat, but that's also my delete button, right?
No, your delete button's above your stat function. The stat function's above the data button. You see that?
Okay, yeah.
So to get into stat, you'd hit your second button first, followed by your data button. That'll take you into stat.
Okay, second and then stat. Okay, I see.
Second and then data. Second data takes you into stat, correct?
Okay, yes.
All right, and you see the one var stat there?
Yes.
Okay, so that's what you're going to do. First, you're going to hit your data button, and it'll bring up your list, correct? And then you just type in the data in list 1. Once you populate list 1, You then hit your second button, followed by your data button to bring up one var stats function. And then you select list one and it'll compute the statistics for list one. All right. But this is what you want to use on the TI-30.
Okay.
It's the same thing as on the TI-34. Buttons are the same, right? So do you think you'll be able to do that or not?
Yeah, hopefully.
Okay, well, number 19 does give us some data. For various countries. And what I don't like about this is I can't get it all on one page unless I zoom out a little bit. Can we see all these prices here, right, on one page? Or I think we can see them all. All right, so just enter all this data into like list one. And then just use your one var stats function to compute the standard deviation of these gas prices. Okay. So let's see if we can use our TI-34, TI-30, or even if you got a TI-84, it works essentially the same way. Does anybody got a TI-84 in this class? Anybody got a TI-84?
I do.
All right, on the 84, what you do is you hit your stat button, select edit. So you hit your stat button and select edit, hit enter to go into the editing mode. And you got your list there. You see that? If you got any garbage in your list, you can move your cursor up onto the list name, hit clear, followed by the enter button, and it clears the whole list out. So just go ahead and put those average gas prices in list one. And when you get done, you hit second mode to quit. Then you hit your stat button again. Go over to calculate. And you got your one var stats function there. The same function that the TI-30 and 34 has. Activate it, and you'll have to put the list name in here. Usually the default value is list one. So make sure you put your data in list one. Leave these fields blank, go down to calculate, just hit calculate, and it will come up with, you know what I'm saying, all your statistics, okay? Does that make sense there? So that's what you'll do
Yeah.
with your 84 calculator, okay? So let's see if we can find the standard deviation a little bit quicker this time without having to go through all those laborious calculations using that table there, right? So we'll call this problem classwork 2 here. All right, classwork 2. Okay. All right, so I entered all these data values in list one here and on the TI-34 here. And let's see here. So I entered all the observations into list one. You can see them right here. And then what I did, after entering all these observations in list one, I hit second data. And I did one var stats for list one. And I got a standard deviation of about 2.34. Anybody get that standard deviation? 2.34?
Yes.
Okay. So that's what the standard deviation gas price would be. And so you can see that on average, the average gas prices in that list tend to stray about 2.32, was it? 2.3 units away from the mean of those average gas prices. Okay. Now here's an interesting situation here. This is a golf course, and it's looking down on a particular hole of a golf course. This yellow over here is probably a sand trap, and the light green here that has the black hole on it is called the green. The black hole, of course, is where you want to get the golf ball into. All right. And these are shots by two different golfers from probably the same distance away from this hole. Several different shots by the same golfer. Again, both golfers were set the same distance away from the hole. Which golfer here appears to be more consistent in trying to get the golf ball in the hole? Pat or Ron? What do you think?
Ron.
Ron. Yeah. Because if you were to take the time and measure all of these distances between these golf balls and the hole, you got all these different distances. You see that? And if you would build a data set with all these differences here for Ron and also for what? For Pat. Whose standard deviation distance would be greater? Pat's or Ron's?
Pat's.
Pat's. That's right. The standard deviation distance of Pat's ball location versus the hole location would be, we would expect it to be greater than the standard deviation of the distances between the balls for Ron and the hole that we were trying to get the ball into. And that would be true too. You can see that Ron is a lot more consistent here in general because these distances for Ron all are very synonymous with each other for all these different ball locations. Whereas for Pat, these distances are all over the place. I mean, this ball is a whopping distance away from the hole, whereas this ball is, fairly close to the hole. Okay. So there's a lot more variability with Pat's shots versus Ron's shots. And with any game, ladies and gentlemen, the key to being successful in any sport is to at least be consistent. Okay. Consistency is the key. And the only thing that increases your consistency at any game is a lot of practice. So yeah, you can see that Ron's consistency with his game is much more pronounced than Pat's consistency. And we're assuming, the key assumption is that both these players, were the same distance away from the hole, same angle away from the hole, under the same weather conditions. That's a key assumption too. Same weather conditions. If all those factors were the same or held constant, you can see definitely Ron was the more consistent golfer in this case. Okay. All right, so yeah, by comparing two or more data sets, by comparing the variances or standard deviations, you can definitely see the differences that exist with consistency of your data observations. More consistent data sets are ones where the data values tend to clump up very closely around the mean, as opposed to data sets where you have a large amount of dispersion, where your data points are far away from the mean on both the upper side and the lower side. All right. Okay. Now, I think there was one more interesting thing here. Here's an interesting investigation. We have enough time for this because I'm going to keep the data set small. And you can use your calculator here for this. Please do. Please use the one var stats feature. How would suppose I had a small data set here. Suppose my data set was like 5, 10, 15, 20, 25, okay? Let's find the standard deviation of this data set right away here, okay? So let's find the standard deviation. Just go ahead, put that very small list, the data into a list, and it says find the standard deviation. All right, let's just do that. That shouldn't take too long. Oh, by the way, with your calculator, how do you delete values in a list? Well, you just put your cursor at the top and keep hitting your delete button in fast succession. That will clear out a list. It'll clear it out very quickly. Okay. All right, just enter these values into like list 1. And use the one var stats feature to find the standard deviation. Standard deviation is about 7.9. I'm going to write that down. 7.9. Now, here's an interesting thing. Suppose we take the same data set, ladies and gentlemen, we add 5 to every data point. We add 5 to every one of these data points. So the first data point becomes 5 plus 5 or 10. Second data point is 10 plus 5 or 15. 20, 25, 30. Let's find the standard deviation now of this data set, which is this data set shifted upwards by 5 units, where we added 5 to every data point. So let's type in this new data set here. Now, it doesn't matter what list you put this new data set in, list 1 or 2, or it's entirely up to you. The bottom line is we want the standard deviation of this new data set here. You know what I'm getting for the standard deviation? I'm getting 7.9. Why do you think these standard deviations are the same? These data sets are different. Why is it logical that these standard deviations would be the same?
Because they only went up by 5.
Every data point went up by 5. Do you agree?
Yeah.
So look at the difference between these two data points is 5. Well, guess what? It's still a difference of 5 here. The difference between the max and the min is 20 here. Well, guess what? It's still 20, the difference between the max and the min. So, ladies and gentlemen, since we added 5 to every data point here, relatively speaking, nothing has changed. Okay. The standard deviation is still the same. No change. Ranges are still the same. The distances between adjacent data points are still the same. So we would suspect that the standard deviation should also be the same. All right. Now, what if we take this data set and we multiply every value by 5? Let's try that. So we'll have 5 times 5 or what? 25. 5 times 10 is 50. 5 times 15 is going to be 75. 5 times 20 is 100. And 5 times 25 is 125. Let's find the standard deviation of this new data set now. Is the standard deviation the same for this new data set here? Is it the same now? Oh, it's a lot different. I'm getting something a lot different here. In general, I'm getting about 39.5.
That's what I got.
Hey, check this out. If you take this standard deviation from this data set and multiply it by 5, guess what you're going to get? You're going to get 39.5. The standard deviation of this data set, which came from every data value that came from multiplying all these data values by 5. So we're investigating something very simple, very, very obvious here, ladies and gentlemen. The bottom line is this: if you have a data set, you add the same number to all your data observations or subtract the same number from all data observations. Is that going to change your standard deviation? The answer is no. But if you have a data set and multiply all your observations by the same number, it will change your standard deviation. In fact, the new standard deviation is going to be the number that you multiplied all these observations by times the standard deviation of the original data set. And if you were to divide all these numbers by 5, I bet the standard deviation of that new data set would be this standard deviation divided by 5. You agree? So that's kind of interesting to note. So a standard deviation is immune to adding the same number or subtracting the same number from every observation in your data set. But it is not immune in the sense that it does change. If you were to multiply every data value in your data set by a number or divide every data point in your data set by the same number, your standard deviation then does change. So that's just interesting. I just thought I'd pass that on to you. Okay. All right. All right. Well, today we looked at how to compute a measure of dispersion, most notably the standard deviation, which gives us a little bit more robust picture as to what's going on with your data set, not only in the sense of its measure of central tendency we talked about 2 days ago, but also now we know, how to determine whether a data set is very dispersed versus not dispersed. Okay. And this transfers over into everyday life, especially in the sporting industry, as far as consistency is concerned. Okay. Smaller standard deviation, the more consistent your data is. The larger standard deviation, the less consistent your data is, the more dispersed it is. Next week, we'll look at measures of position, namely quartile values and percentile values. You probably heard the old adage, so-and-so scored in the 99th percentile on the SAT test. Is that good or bad? If you score in the 99th percentile, we'll find out next week. And if that is good, how good is it? What does it really mean? So we'll look at measures of position next week. With that, I will let you go. I'm going to open up that quiz. Like I said, I'll get that open and it'll be due by midnight, December 11th. If I need to extend the due date, I will let you know and update the schedule. All right, ladies and gentlemen, have a great weekend. I'll be on the line for a couple of minutes if you have any questions or concerns.
I do have a question. Are you going to upload the videos today as well?